In this video, we're going to use a chain rule to work out the partial derivative of w with respect to u. So given w equals this and xyz equals this, we need to work this out at this particular point. So the first step is to try and understand what's going on. So if you look at w equals this whole thing here, everything's written explicitly in terms of x, y and z. So you've got these three variables. When you put it into the function, it will spit out the value w, and u and v will determine where the particle should be, meaning u and v will determine the x location of the particle, the y location of the particle, and the z location of the particle. So for example, let's say you've got a particle moving around like this in 3D space, x, y and z. So there's this there are these two independent variables, u and v, which will determine where the particle should be. You're always going to know the x, y and z location of that particle. So you always know the x, y and z location of that particle, and everything is driven in terms of u and v. And then once you know the position of the particle, you put it into the machine, if you like, this machine here, and then it will spit out a value w. So let's say the particle is here, it will spit out the value -1, say, or let's say you're currently here, it will then spit out the value, let's say 2, and so on. So we want to know how w changes with respect to just one independent variable, u. So you could, if you want to, work out this with respect to v if you wanted to, but in this video we're just going to do it with respect to u. So the first step, using the chain rule. So using the chain rule, if you want to work out the partial derivative of w with respect to u, then consider in the x direction, the y direction and the z direction. So in the x direction, you've got to times it with the partial derivative of x with respect to u. So what that means is, if you look at our machine was like this: w, x, y and z. So here you've definitely got partial derivative w with respect to partial derivative of x, as opposed to dw dx, say. This is not the case because you've got three variables coming into the machine. And then when you look at this part, if you look at x, you've got u and v, two independent variables. Two independent variables will determine where the x location of the particle should be. So if you just look at this bit here, what you've got here is really a case of u and v coming into the machine, and then it will spit out the x location of the particle. So here it's going to be a definite partial derivative of x with respect to u, as opposed to dx du, because here you've got two independent variables coming in to determine the x location. So this is a partial derivative of x with respect to u, and the same goes with y, because u and v will determine the y location of the particle, because you've got two variables coming into the machine to determine the y location, and the same goes with the z. So the chain rule gives us this here. Okay, so now it's just a matter of computing this. So take the partial derivative of w with respect to x. So with respect to x. So when you differentiate it, when you take the partial derivative, it will be y. It will be y, and then it will be z. And then for this bit, look at x. Take the partial derivative of x with respect to u. So u is your variable, v is just a constant. So when you differentiate it, it will just be this one here. That's why this one here is this one here. And then partial derivative of w with respect to y. So now y is your variable, y is your variable. So when you differentiate it, it's just x, z. It's just x, z. And then for this bit, have a look at the y. Partial derivative of y with respect to u, that's just 1 here. So that one there would be here. And then now look at look at z. So z would be y plus x. Would be y plus x. So for this bit, let's look at the z. So look at the z. Take the partial derivative of z with respect to u. So when you differentiate, so u is a variable, z is a constant. So when you differentiate it, it's just well, v is a constant. So when you differentiate it, it would just be v. So that would then give us this thing here. But we don't want the answer in terms of x, y, and z. So we would put this into the y. That would then give us this thing here. We would put this into the z. That would then give us this thing here. We would put this into the x. That would then give us this. We would put this into the z. That would then give us this. Put this into the y. That would then give us this. Put this into the x. That would then give us this, and you got your v here. Tidy this whole thing up. It will then give you this. So it will then give you this. So the partial derivative is given by this, but we want to evaluate it at this specific point where u equals a half and v equals 1. So we would put this into the u, so that would then give us 1, and put this into the u and put 1 into the v. That will then give us 2. So the final answer is 3. Okay.